Today we're going to continue looking at the derivatives and graphs and what the derivatives, the first and second derivatives, tell us about the graph of the function. So if you recall, the sign of the first derivative tells us about the direction of the function. And the sign of the second derivative tells us about the concavity of the function. Since the second derivative is just the first derivative of the first derivative, the sign of the second derivative tells us about the direction of the first derivative. So here are all the relationships between the first derivative, the second derivative, and the function with regards to sign, direction, and concavity. Last time we started looking at this function, x cubed minus 9x squared minus 48x plus 52. We wanted to, we found the derivative of the function and set the derivative equal to 0. And we found out that the first derivative is equal to 0 at -2 and 8. So that tells us that the function is flat at -2 and 8. So this tells us that f is flat when x equals -2 and when x equals 8, because the first derivative is equal to 0 at those points. So f is flat when x equals -2 and when x equals 8. And this all comes from solving the equation f prime of x equals 0. That means in between -2 and 8, or when x is less than -2 or more than 8, the first derivative will always be positive or negative. Since we know a thing or two about polynomial functions, and we know that the graph of this polynomial function, since it's cubic with a positive leading coefficient, we know that the graph has to drop down, go to -infinity when x goes to -infinity, and positive infinity when x goes to positive infinity. In between these 2 points, or in these 2 parts, I know I have to make the function flat twice. So I have to make the function flat, and then the function is going to have to be flat again, so we can see what's going to be happening at each of these points. At -2, it looks like we're going to have a little local maximum, and at 8, we're going to have this local minimum. So our intuition and our knowledge of polynomials tells us that before -2, the first derivative is going to be positive. Between -2 and 8, the first derivative will be negative because the function is decreasing. And after 8, the first derivative should be positive because the function is increasing. Let's verify that by choosing some values from these ranges and plug them into the first derivative to find out if they're positive or negative. Since f is flat when x is equal to -2 and x is equal to 8, the first derivative will be positive or negative when x is not those values. So f will be increasing or decreasing when x is not those values. So what we're going to do is I'm going to pick a value, say less than -2, and I'm going to look at the value of the first derivative at a point here. So I'm going to choose x equals, I need something less than -2. So I'm going to choose -10. -10 is going to be my representative for all the x values that are less than -2. And I'm going to find f prime of -10. So f prime of -10 will be 3 times -10 squared minus 18 times -10 minus 48. Now our expectation is that this should be a positive value because I know the function is increasing because of what we know about polynomial functions. But we want to see that happen. Oops, too far. in the numbers here. So this is going to be 300 plus 180 minus 48. So it'll be 300 plus 180 minus 48, which is positive. So f prime is positive, and so that tells us that f is increasing, just as we had suspected. Now we can choose a representative between -2 and 8. And I'm going to choose 0. 0 is going to be the representative for all the x values that are strictly between -2 and 8. And we're going to test f prime of 0. So I'll have 3 times 0 squared minus 18 times 0 minus 48 is -48, which is negative. So f prime is negative for all the values of x between -2 and 8. Since f prime is negative in this interval, it is decreasing on that interval, just as we had suspected, just like we had foreseen. And then once again, for x greater than 8, I'm going to choose a representative to represent all the values of x greater than 8. And I can pick whatever I want. I'll pick 10, mostly because it's easy to plug in. And I'm going to test the sign of f prime of positive 10, which will be 3 times 10 squared minus 18 times 10 minus 48. So it'll be 300 minus 180 this time, and minus 48, but this is still positive. So as long as x is greater than 8, f prime will be positive. And that tells us that f is increasing. Another thing that we can point out about the function, at -2 is where the function changes from increasing to decreasing. So we call this a local maximum. We say f has a local maximum when x equals -2. So we would say that f has a local max at -2. Because the function is changing from increasing to decreasing. So it must max out at -2 when it goes flat. And then since f changes from decreasing to increasing when x is equal to 8, we would say f has a local minimum when x equals 8. We refer to these points as local maximum and a local minimum, because when x is equal to -2, we're at the highest point in a small neighborhood around -2. When x is, we know that x goes to infinity. As x goes to infinity, f of x also goes to infinity. So whatever the value of the function is when x is -2, there are larger values of the function. But in a small neighborhood near x equals 2, -2 is where the highest point is, the highest point occurs. And what similarly, this at -8 we have a local minimum. It's the lowest point in a small neighborhood around 8. But it's not the lowest point on the entire graph. The local maximum is the highest point in a small neighborhood around -2, but it's not the highest point on the graph. It may be the biggest kid in the school, but it's not the biggest kid in the city.
Professor, so how do you find like the maximum or global maximum, I shall say?
So if we wanted to find a global maximum, that would be the highest point for any value of x. For this particular function, if we're not restricted to some closed interval, there is no global maximum or global minimum, because there are points that are higher than our local maximum. If we had some endpoints, if I said only consider values of x between -10 and 10, then we could check those endpoints to see if they're higher or lower than the local maximum or local minimum. So that's how we could find global maximum or a global minimum. Any other questions?
Yes, Professor Leach, I have a question, please.
Mhm.
On the example, we have f of x equal x to the q third power
Yes.
minus x. And then below that, we have the f prime equal 3x squared minus 18x minus 48.
Yes.
And on the right, we have f prime of x equals 0. Then we factor it out, we have x minus 2, x equal 8. Could that be 0? It have to be 0 when we set up this equation, or could it be f prime of x equal other number?
What we're looking for is the points where f is flat. So we wouldn't put something other than 0 because we're trying to solve this equation. I wanted to find out where f is flat so I could figure out where f is increasing or decreasing.
Okay.
So there's no point in solving f prime of x equals 1 or some other number. I want to know where f is, the function f is flat. I need to look where f prime is equal to 0.
Okay, thanks. I put it in my head. Got it. Thanks.
So another thing to note is that we can look at the second derivative, and the second derivative can tell us if we have a local maximum or a local minimum. So the second derivative tells us about the concavity of a function at a point. If the second derivative is positive, the function is concave up, and if the second derivative is negative, then the function is concave down. So we know that there's a local maximum when a function changes from increasing to decreasing, and a local minimum when the function changes from decreasing to increasing. That's first derivative knowledge, because we're looking at the direction of the function for changes in direction of the function. But if we have the second derivative available, if we look at the second derivative, so f prime is 3x squared minus 18x minus 48. The second derivative, f double prime, will be 6x minus 18. If I plug -2 into the second derivative, the value comes out. Let's just see what happens. If we look at f of -2, we get 6 times -2 minus 18 is -30. Which is less than 0. So if I add another line here for the second derivative, the second derivative when x is -2 is negative at that point. So the function f is concave down at x equals -2. So if the function is flat and concave down, we must be looking at a local maximum. Then we could do the same thing at 8. If we look at f double prime at 8, we get 48 minus 18, which is positive 30, which is greater than 0. So when x is equal to 8, f double prime is positive, which means that the function f is concave up. If a function is concave up and flat at a point, we must be looking at a local minimum. Any questions? So,
In the top right,
uh-huh.
This is going back a little bit, but you did some factoring there.
Yeah.
I was wondering, like, how does that work exactly? I'm kind of confused on factoring what you did here.
I need to find factors of negative 16 that I can make a negative 6 with. Negative 16 is 2 times 8, and 2 minus 8 is negative 6. So that's how we get factor.
Oh, okay. So you use the it's like the triangle.
I think triangle is one of the things that people do to factor. So the other thing we could do, other thing to note about factoring, since it's come up. So we're looking at x squared minus 6x minus 16. So we want to find factors of negative 16 whose sum is negative 6. So we could think of factors of negative 16. It's 1 times 16, 2 times 8, 3 times, nope, 4 times 4. These are the integer factors of 16. And now I know I'm done because I've reached 4 times 4. I've kind of wrapped around. And I just got to make sure I have different signs because they have to have multiply out to negative 16. And the sum is going to be negative 6. So then I just went back and said, well, 2 and 8 can be combined to a negative 6. If I make a negative 8 and a positive 2, that'll make a negative 6. So that tells me one of my factors will be x plus 2, and my other factor will be x minus 8. Another way we think about this problem is, in fact, one of the things that we're about to find is where the vertex of this parabola is, and we can find that by completing the square. So we can also read this x squared minus 6x minus 16. If I have an x squared minus 6x, I know that if the next term is a plus 9, then that will factor out to x minus 3 squared. So x squared minus 6x plus 9, these three terms will factor out to x minus 3 squared. But it didn't say plus 9, it said minus 16. And I can't just add 9 to a polynomial to make the things work out. I'd have to subtract 9 to balance things out. So I could rewrite this polynomial as x minus 3 squared. Why green? X minus 3 squared minus 16 minus 9 is 25. This tells us a few things. I've got a vertex at 3, negative 25, and the parabola opens up, so I know that there are going to be 2 solutions. So reading this, we see a vertex at 3, negative 25, and we also know that the parabola opens up. So we know, since the vertex is below the x-axis and the parabola opens up, we're going to have two solutions. So we know we should be looking for some solutions. And if we want to solve this equation, if we want to find those two solutions, if we set this equal to 0, then x minus 3 squared is equal to 25. So x minus 3 is equal to plus or minus the square root of 5. So x is 3, square root of 25, which is 5. 3 plus or minus 5. So 3 minus 5 is -2. 3 plus 5 is 8. So we could also solve this way by completing the square. It's kind of handy to do things this way because not all polynomials are factorable over the integers. So in this case, we want to find factors of -16 whose sum is -6. This is because this problem was built for us to be able to factor the polynomial. But polynomials that we encounter in the wild are not necessarily going to be factorable. If I change this to say x squared minus 6x minus 17, all of a sudden it's not factorable over the integers because I can't find factors of -17 whose sum is -6. I can't find rational factors of -17 whose sum is -6. So this is not factorable. A lot of times before we said things were just not factorable and that was the end of it, but it's not factorable over the integers, over rational numbers.
Professor Leach, so if you use quadratic formula, does that count as factoring or no?
The quadratic formula is not factoring. The quadratic formula is a shortcut to completing the square. The quadratic formula is built to get at solutions quickly with lots of errors, unless you use a machine to get at them quickly. So if you're going to solve using the quadratic formula, use a machine. So make sure, I don't know if this has an app, but you might have to program your own quadratic formula into your calculator. Then again, if you want exact values, then you're gonna have to do that. But the quadratic formula is a shortcut to completing the square. Notice if I take x squared minus 6x minus 17, I can do the same thing. I know that leading with an x squared minus 6x, this will become a perfect square if I complete it with a plus 9. But we can't just add 9 to stuff. We have to subtract 9 to balance out. So those first 3 terms work out to x minus 3 squared. -17 minus 9 is going to be -26 this time. And now we can also see that it's not factorable. Our vertex is at 3, -26, and the parabola opens up because there's a positive. So we know we're going to have 2 real solutions. Since 26 is not a perfect square, we know we're going to have 2 real irrational solutions. So if we go to solve, we're instead of the 25, we have x minus 3 squared is equal to 26. So x minus 3 is plus or minus the square root of 26. So x is equal to 3 plus or minus the square root of 26. Now, for the most part, we're taught to either try factoring first and then just default to the quadratic formula because everything's formula driven, and we want to make sure that you don't understand or picture what's going on, that you just grind out to the answers as if getting the answers is the important thing, and it's totally not. I think we use the quadratic formula a lot because it's easy to demonstrate proficiency in your simplification skills and your ability to remember the formula. But one of the things that we miss out on is when we complete the square, we get all kinds of extra information just by looking at x squared minus 6x minus 17. With a +9 and a -9, I know I'm going to have a -26 out here. So now I know that the vertex is at 3, -26. And I know parabola opens up. And so therefore we'll have two solutions, two real solutions. We always have two solutions. And since it's a -26 is not a square, we know that they're going to be irrational. So the argument can still be made that this is going to be slower than using the quadratic formula. But then the counter argument to that is like, oh, well, then why are you writing out your quadratic formula if speed is the question? And then, of course, the counter to the calculator is like, oh, well, what if you're on a desert island and you don't have your calculator? If I'm on a desert island and I don't have my calculator, I'm more concerned about food, shelter, and water than I am about solving quadratic equations. Tom Hanks didn't save himself with math. He saved himself with buoyancy. So the problem that I have with quadratic formula is that it ignores a lot of stuff that's going on. So if we just are trained on a steady diet of quadratic formula and we look at this problem, we might just like jump into the quadratic formula because we've been programmed to do that because someone thought we were a robot. But this one, if we think about completing the square and we become proficient in completing the square, we know that we're not going to have any real solutions here. Because when we complete the square, I'll need an x squared minus 6x plus 9 plus 17, and then minus 9, we can see that the constant term in the vertex form is going to be positive. So the vertex is going to be above the x-axis, and the parabola opens up because of the positive leading coefficient. So we have no real solutions. Uh, 17 minus 9 is what, 8? So we see that the vertex is at 3, 8, and it opens up. So therefore, we have no real solutions.
Professor, so does it have to be like a 3 or like two negative 3s? Or can it be like, let's say, -2 and -4?
We could factor, what we're looking for is a square. When we complete the square, we're looking to make this an x minus 3 squared. Because what we want is, if we're solving an equation, we want one instance of the variable so we can perform inverse operations in reverse order. But if you want for some reason this to factor out to, see, we need to make a -6, x minus 2 times x minus 4, you can just figure out what this constant would be and then balance it out. That would be a strange choice for factors. It would be, we want the x minus 3 squared, but we can really write this however we want. Any questions?
Yes, Professor Leach. At the very bottom, is the vertex 3, 8?
Yes.
And above that, it said x minus 3 with the square to the power. So which means at 3, there's parabola, correct? I get that, but how do you know it's up,
It's a positive leading coefficient. So the coefficient of x squared is 1, and that's positive. And so the parabola opens up. So it's going to be.
So it's exactly the same, the one vertex on the top there.
Yep.
3, -26, the coefficient is positive. That's why it's up, correct?
That's why it opens up, yes.
Right, thanks.
So in the previous one, it opens up. The vertex is at 3, -26, so it's way down here, and the parabola opens up. So that tells us that we're going to have 2 real solutions.
Oh, okay,
The fact
that's
that
what
it's a
it
20,
means.
that 26 is not a perfect square tells us that they're going to be irrational.
Okay, got it. Thanks, Professor Leach.
Any questions? This happens a lot in calculus, and usually when this comes up and we start solving equations, I always bring this up about completing the square and what quadratic functions look like, mostly because most of my students come through haven't been trained on quadratic formula because you've been given this false impression that coming up with the solutions, coming up with a 3 plus or minus the square root of 26 is the point of the problem, and it's not. This is even a better form with the 3 plus or minus the 26, square root of 26, because if we think about where those, we think about the vertex, this point at 3 negative 26, that demonstrates, that shows us the middle, the axis of symmetry. And that axis of symmetry happens when x is equal to 3. And then the plus or minus the 26 is because there's symmetry. And so we have a plus square root of 26 on this side and a minus square root of 26 on this side. So that's why up here we have 3 plus root 26, and down here we have the middle 3 minus root 26. So I prefer this form. I prefer this vertex form because it also shows me the symmetry. I get the middle and I see how far apart the x-intercepts are going to be. Any questions? So by writing the quadratic formula the way that we write it, we miss out or we ignore one of the great pieces of a parabola. We ignore the fact that parabolas are symmetric about a vertical line through their vertex. Or if it's x equals y squared, a horizontal line through their vertex. Any questions? So I guess the only real part of the quadratic formula I object to is the all over 2a part, because it's always written as one fraction. And it probably should, we should probably write it at opposite of b over 2a as the middle, and then put the plus or minus the b squared minus 4ac all over 2a. Because then here's the middle, and here's how much it goes out on either sides. So just splitting it up into two terms like this emphasizes a middle and then a plus or and a minus. So it shows us in the formula the symmetry with the plus or minus from the middle. In the formula, we're emphasizing the symmetry of the solutions, not just grinding out the stupid solutions, because those don't matter. You know what I mean?
One question for Professor Leach.
Yeah.
Back to the leading coefficient. If
Uh-huh.
the positive, negative, that we would able to tell is up or down already. Am I right?
Correct.
Okay. You just wrote down the quadratic here. X equal minus b over 2a plus minus.
Yes.
Is that a good equation to use or not? I misunderstand.
So I'm just thinking about the quadratic formula, and the quadratic formula combines the terms and puts everything over 2a. And for me, that hides the symmetry that's happening. It puts the plus or minus above this whole fraction.
Mm-hmm.
But if we just split the quadratic formula up into two terms, we can see where the middle is, and we can see the symmetry. in the formula, we can see the symmetry in the numbers, and we can see how these two solutions are related. And it emphasizes that this x minus 3 form has 3 at the center, at the middle. It shows us where the symmetry is. That's the point I'm trying to make.
Yeah. Thanks, Professor Rich.
Because if the point is just solving equations quickly, then we should use a machine for that. So
Okay.
I have a quadratic formula. If I run a quadratic formula on, that's the 3 plus or minus 26, I have to put in 1, -6, and negative 17, and it can just barf out the answers.
I got it. When I see that equation, I hate it, you know. But
Well, you're gonna have to get good at completing the square.
got it.
Here's
Thanks,
another
Professor.
thing that we notice. When the vertex was at 3, -25, my solutions were at -2 and 8. And what happens when I, and that was when x squared minus 6x minus 16. When I drop this down by 1, when I subtract 1, it moves the x-intercepts a little bit farther apart. So when I look at these answers, I know that we were really close to, since 17 is just 1 less than the -16. -16 would give us factors of 8 and -2. So if I run this again with a 1, a -6, and a -16, they're my solutions at 8, -2. So when I change the constant c to a -17, I know I'm going to go from a difference of 5, the square root of 25, to the square root of 26. And I can watch those x-intercepts spread out. Any questions? So a quick detour into polynomials. So also important to note that when we say something is factorable, a polynomial is factorable or not factorable, at this point in our careers, when we say factorable, we mean factorable over the rational numbers. Because the fact is, x squared minus 6x minus 17 is factorable, but we need irrational numbers to do it. So x squared minus 6x minus 17 is factorable, but the two factors are going to be irrational. We have a 3 plus the square root of 26 and a 3 minus the square root of 26. But if I wanted to factor this, I could say it's x minus 3 plus root 26 times x minus 3 minus the square root of 26. It's the same thing that we did when we found x equals -2 and 8. X minus a -2, x minus an 8. And if we multiply this polynomial out, these factors out, we'll come up with x squared minus 6x minus 17. Let's do everything. First, outer, inner, cancel that out. Yep, that's what we get. Any questions? How's everybody okay? I think I mentioned at the beginning that one of the challenges that you face when you're in a calculus class is the algebra that's involved. Not just the algebra in manipulating things, but all the algebra that you don't remember. Now, when students come to my class, it's always, the blame is always placed on teacher. There's like, oh, my teacher didn't teach me that. And meanwhile, when I call up your other teacher, they're like, oh, I totally taught that. They just don't remember. And then I'm like, I know, right? I'm just kidding. I'm not going to call your old math teachers. Any questions? Comments? Snide remarks? All right. So some interesting polynomial stuff. Oh, there's another thing and another thing. We know that there are no real solutions to when we had x squared minus 6x plus 17. Maybe we saw that right away. 17 was super obviously much more than a 9. And that's what tells us that if we're gonna have real solutions or not real solutions. But that we only have those kinds of instincts, not because of this b squared minus 4ac stuff, but if we look at x squared minus 6x and imagine the x minus 3 squared with a plus 9. So a plus 9 will put the vertex at 0, and anything more than that will move the parabola up. When it's less than that, we'll move the parabola down. So another thing to note is that if we're looking for the zeros here, we know that they're not real solutions, but we can solve in the same way we did before. X equals 3 in the middle, plus or minus the square roots of -8. So 3 plus or minus 2i times the square root of 2. So proficiency will still get us a better result than the quadratic formula. Is not to say that you're allowed to forget the quadratic formula. You still need to remember the quadratic formula, and you still need to be able to derive the quadratic formula by completing the square. But if the argument is there are better ways than completing the square, your argument is pretty much don't know that thing. Don't bother knowing that thing. And y'all are adults now. And so all the school that you go to now is entirely optional. You're here by choice. So when it gets annoying and you're like, oh man, that Leach sure is a jerk, remember, you brought this on yourself. You know what I mean? All right. Any questions, comments, snide remarks? Tomorrow we have a question about chapter 3, section 8, which, but I knew this quadratic function thing was coming today. This parabola bit was coming today. So I didn't save enough time for that. All right, so continue doing some catch-up work before we start moving on to new things at the end of the week. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.